It's my pleasure to present the paper Automation and Population Growth, Theory and Cross-Country Evidence, which was written together with Anna Abeliansky, who is at the Vienna University of Economics and Business. The motivation for this paper is the following. So we've observed substantial demographic changes over the last decades, particularly in high-income countries, with fertility rates falling strongly and in many countries even below the replacement rate that would be required in the long run to keep the population steady. This implies that workforce growth has slowed down in many countries, and in some countries it even has turned negative, for example in Japan. And in Europe, the media at the moment talk a lot about widespread labor shortages actually, and that firms have a hard time finding suitable workers. At the same time, however, we've observed that automation has progressed quite enormously, and some policymakers and commentators have voiced concerns that mass unemployment would be the consequence of automation. If automation takes over, basically, then we have so many workers without jobs, and this would create mass unemployment. So in a nutshell, we are basically at the same time afraid of labor shortages and mass unemployment, which is kind of difficult to reconcile. Now, what we want to do with this paper is to provide an explanation for why these two concerns may be present at the same time. Now, the literature on automation and its economic consequences has seen its own exponential growth over the past decade. Here in this presentation, I don't want to go into the details and refer you to other lecture casts on this topic and the book that I've written with David Bloom on automation and its macroeconomic consequences. But what can be said is that the literature on the driving forces of automation, and in particular on the role of demographic change in this regard, is not yet huge. Together with Agnieszka Geringer, in 2017, I've published a paper in which we argue theoretically and empirically that population aging incentivizes investment in new technologies. And Asimoglu and Restrepo published a paper in 2021 where they argue that this force is also present in with respect to automation. Now, how we want to contribute to this literature is to provide a simple framework that shows the incentives to automate and how these incentives change in a standard economic growth model of the Solow type, and then analyzes the extent to which a declining population growth rate changes these incentives or reinforces these incentives, basically. And afterwards, after sketching these theoretical mechanisms in the background that are operative even in a very standard framework, we provide cross-country evidence that supports these theoretical predictions, and basically this evidence shows that a slowdown of population growth indeed incentivizes automation. So after having sketched out basically what we do, let's go into the details of the simple framework. We assume that time evolves discretely and is denoted by lowercase t, and that we have three production factors. We have human labor, and we have two types of capital. Traditional physical capital, these are the machines, assembly lines, production buildings, and so on, that show a certain complementarity with the production factor human labor. So the Cobb-Douglas production function actually describes quite well how traditional physical capital and human labor interact. So without human labor, for example, machines would not run and assembly lines would not run. However, there is a certain form of capital, that's automation capital, in the form of robots, 3D printers, and so on, that do not require labor input and are basically, in the basic version of the model, a perfect substitute for labor. The results actually do not hinge on this strong assumption, but basically it suffices to have a high elasticity of substitution between automation capital and human labor. Now, the central point is that automation capital is then a competitor on the labor market for human labor, but at the same time it is accumulated according to the standard savings behavior in neoclassical growth models, so it belongs to the capital owners. And that also means that while it puts downward pressure on wages, it increases the return to capital broadly defined, so the traditional physical capital and automation capital, which basically leads to an increase in the capital share of income in an economy. Then we assume that households save a constant fraction S of their income and invest this either in traditional physical capital or in automation capital. Again, the results do not depend on whether this fraction is exogenously given or endogenously determined by households. The only difference would be that in the endogenous case, S would be a function of the time preference rate of households or the discount factor, but it would also be between 0 and 1 as it is when we assume a constant saving rate. The advantage of assuming a constant saving rate is in this context basically that we have data on the saving rate or on the investment rate in the empirical part of the model so that we can compare the predictions of the model directly to the results in the regressions. Now we consider a production function that is without automation capital of the Cobb-Douglas type. So we have total output in the economy, YT, is produced with human labor LT with an output elasticity of 1 minus alpha, and with physical capital KT with an output elasticity of alpha. However, now we have a perfect substitute for labor, PT, which we interpret as automation capital. And now already a lot of effects become visible. So this automation capital helps to overcome the diminishing marginal product of traditional physical capital. So capital broadly defined would have a constant return here. And if you use this production function, the Solow model, what you would get is that there is the potential for perpetual long-run economic growth even without technological progress. For this, I can refer you to the corresponding lecture cast in the list, Automation in the Solow model. And the second prediction is that if automation capital accumulates, then the labor share is declining. So this basically describes what we've observed since the 1980s, a declining labor income share. Now, however, we are not so much interested in the long-run implications of automation and more in the determinants of automation, in particular demographic changes. So the first thing that we do to arrive at the model that explains what drives the accumulation of automation capital, we compute the factor rewards. And the factor rewards are the wage rate as the derivative of the production function with respect to the production factor labor, L, so that's the marginal product of labor. Then the interest rate on traditional physical capital is the derivative of the production function with respect to KT, and we subtract the rate of depreciation that we assume also capital is subject to depreciation. And also automation capital has a return, so that's the derivative of the production function with respect to PT, and it also depreciates. And what we have if automation capital and workers are perfect substitutes is that the rate of return on automation capital must be the same as the wage rate, basically. Now, what we see here is we have the standard effect that as traditional physical capital accumulates, the wage rate would go up and the capital rental rate would go down, but it's the opposite for automation capital. So if automation capital accumulates, this puts downward pressure on wages, but upward pressure on the interest rate. So that's what we observe from the factor rewards. So now we assume that there are rational investors in the economy. So they make the decision of whether they want to invest in traditional capital or automation capital. And of course, this implies that in an interior equilibrium where both of these investment vehicles attract investments, the rate of return of both saving vehicles must be the same. And since the rate of depreciation was assumed to be the same, this also implies that the interest rate that these two assets pay have to be the same. So therefore, we can set RKT and RPT equal to each other. And then a lot simplifies and we can express the automation capital stock in the economy as a function of parameters and the traditional physical capital stock as well as the number of workers in the economy. And what we see immediately is that if there is more traditional physical capital, so KT is higher, that would imply in equilibrium that also the stock of automation capital is higher. Ceteris paribus. And that's clear because if we have more traditional physical capital, more assembly lines and machines and so on, then we need to staff them somehow. But if the number of workers stays constant, we can only operate them with robots, basically. So the number of robots would ceteris paribus increase for an increase in traditional physical capital. At the same time, more labor in the economy implies less automation capital in equilibrium. And also this is intuitive. If we have more workers, then the wages would ceteris paribus be lower because the marginal product of labor would be lower, as we've seen previously in the factory wards, right? So that then implies that there is only a lower incentive to invest in automation. If you have many workers in the economy and wages are low, then firms would rather employ cheap workers than invest in perhaps expensive robots. So that's what this no arbitrage relationship, or this consequence of the no arbitrage relationship, tells us. Indeed, the investments in automation depend on the number of workers, and this is exactly the link by which investments in automation later on will depend on demographic properties, or demographic assumptions of this model. Now we put things together. We know aggregate capital in the economy is the traditional physical capital stock plus the automation capital stock. And if we assume full depreciation, then this means that the total capital stock accumulates according to how much is saved in the economy, which is the saving rate multiplied by total output YT. Now we can plug into this expression the production function from one of the previous slides, and then the no arbitrage condition from here. So where we isolate KT to express the whole expression only in terms of PT, so the number of robots. And if we divide this by the number of workers, then what we get is a equation that describes how the so-called robot density, which is the number of robots per worker, changes over time. So we get the difference equation describing the evolution of the robot density. And what we observe here is that this depends on the number of parameter values, in particular on the saving rate. So if the saving rate is higher, then ceteris paribus automation capital would accumulate at a faster rate. And it depends on the previous automation capital stock, of course, and in particular the population growth rate. So what we observe here is that the automation density decreases with population growth. And the intuition is again that in a country where population growth is fast, ceteris paribus, you would have a larger workforce. If you have a larger workforce, the marginal product of labor is lower, wages are lower, and therefore the incentives to automate are also lower. For intuition, compare two countries with each other, one with a very high population growth rate and a high fertility rate, and one with a very low fertility rate and perhaps negative population growth and negative workforce growth. So take Nigeria versus Japan. In Japan, workforce growth is negative, fertility is low, and the wages are comparatively high. So it pays off for firms to invest in automation. In Nigeria, it's the opposite. The population growth rate is comparatively high. Unemployment, particularly among the young, is high. And so you have many workers available and the wages are comparatively low. So you would not, perhaps as a firm, invest in automation, but rather decide to hire workers if you have a production facility there, while in Japan, it's the opposite. Now, what about the robustness of the theory? One assumption that is frequently criticized is the one that there is perfect substitutability between automation capital and human labor in the model, but this can be relaxed quite easily without changing the qualitative insight. So for example, one can use a production function as it is written down here with skilled and unskilled labor, and the assumption that only unskilled workers can be perfectly substituted by robots. So that would then be the assembly line, and workers would kind of work on this assembly line and be perfectly substituted by industrial robots, but then the skilled workers, engineers or whatever, could not be perfectly substituted by robots. Instead, the elasticity of substitution between low-skilled workers and by implication robots and high-skilled workers would be determined by gamma. this parameter of the production function. And physical capital, traditional physical capital, is treated as in the Cobb-Douglas production function before. And if you compute this, do the same computations that we had on the previous slides, you would also still get that an increase in the population growth rate decreases the incentives to invest in automation capital, PT. So from a qualitative perspective, this does not change anything in the model. A second aspect that is often criticized and to which I've already commented upon is the exogenously given saving rate. Now you can endogenize it as in an overlapping generations model by assuming that the discount factor that households face is beta. So beta is the weight they give to future consumption. And then nothing would change except for the fact that the saving rate itself would be expressed by beta over 1 plus beta, which would also be an expression that is between 0 and 1, as is the saving rate. So both of these relaxation of quite strict assumptions would not change anything in the framework. Now the question is whether we see the theoretical predictions in the data. And to get a first impression on that, I've shown here a world map of the automation density, so the number of robots per 10,000 workers in this case, based on the data of the International Federation of Robotics. And what we observe here is that countries with a darker color are the ones with a higher automation density, and countries with a lighter color are the ones with a lower automation density. It's also the case that many countries do not have any entries in the data set at all, but this can be safely assumed to be very highly correlated with using only a few robots or no robots at all in most of these cases. So in general, what we can say is that the automation density is higher in the countries with a darker color. And what we see then is that most industrial robots are employed in the countries with higher incomes, but between them, it's the case that those countries that are aging fastest or having the lowest fertility rates are the ones with the highest automation density. For example, Japan, South Korea, Germany, Italy, and so on and so forth. So at least from this first view on the data, there may be something to the theoretical prediction. We can also look at the league table of the automation density, robot density per 10,000 employees in manufacturing as of 2018. And what we see is that at the top of this list, we have South Korea and Japan with very low fertility rates, followed by Germany and Italy, also with very low fertility rates in Europe. And only afterwards, countries such as the US and so on appear in this list. However, we want to analyze this aspect more thoroughly by estimating the following relationship. So here we have the growth rate of the robot density denoted by PIT head. We take the logarithm and regress it on a constant, the population growth rate, the investment rate, and a number of control variables plus time and country fixed effects, basically. And if our theory holds, then we would expect alpha to be negative, basically. So what are the results? Here we provide the table for the coefficient estimates of the previous regression, and we use different methods for computing the regression estimates. The first column contains the fixed effects estimator, and then the rest of the columns take into account potential dynamic aspects by including the lagged growth rate of the robot density as a regressor on the right-hand side as well. Now, since the data set that we have is rather small, particularly in the cross-country dimension, because many countries do not yet have the data on robot use in the International Federation of Robotics database, we know that the GMM estimates, system GMM estimates in the fifth column here, will be very inefficient, so come with a high variance. And therefore, it's rather recommended usually to use the corrected fixed effects estimator, of which we compute 3 different versions here. What we see is that in all of these specifications, where we have here the control variables, the saving rate, the per capita income, education, and openness, and we include country and time fixed effects in all of these specifications, where in the system GMM specifications, it's estimated in differences, so the country fixed effects wipe out. We see that in all of these specifications, the population growth rate indeed exhibits a negative sign, which is significant at the 5% level in the first 4 columns, and only in the last one it is not. But here again, the reason for this is that the system GMM estimator is quite inefficient in small samples, and one would rather recommend the corrected fixed effects estimator in this case. We also see that the coefficient estimate is smaller than 1, so it's not purely a capital dilution effect that we observe here. In addition, we have this shift of investment away from automation capital if we observe faster population growth because of this higher number of workers, which would put downward pressure on the wage rate and therefore reduce the incentives to automate. So overall, the empirical findings are very much consistent with the theoretical implications. So where does this leave us? We've seen that declining population growth incentivizes investment in automation, and that countries that face more severe demographic challenges in terms of a slowdown in the growth of the workforce or even a negative growth rate of the workforce, they employ more robots. As a consequence, automation and labor shortages may well be explained by a common underlying force. So low fertility rates in the long run explain both workforce shrinkage and therefore labor shortages and investments in automation. And so it may not be a surprise that both of these forces are present at the same time, that the media reports about them, and that people are also afraid of both of these aspects at the same time. The positive implication of all this is that automation can be helpful to overcome some of the challenges posed by demographic change. So automation may be a silver lining on the horizon of what demographic challenges are concerned. Well, thank you for your attention.